Hi, so welcome to Compilers. I'm here to introduce the Compilers course. I'm going to tell you something about the topic and why I find it so exciting and why I enjoy teaching it so much. I'll also introduce you to the textbook, and I'll tell you something about how to be a successful student. And towards the end, we'll touch upon some topics for more general interest. The primary purpose of this talk, however, this pre-recorded lecture, is to introduce you to the course, how it will be organised, and what it's really about. So this course is taught by me, Paul Kelly, and by my colleague Naranker Dulay. We divide the course up in approximately 2 halves. My interest in the course is primarily in code generation and program optimization. And I'll tell you a little bit more about that as we go forward today. Naranker is covering syntactic analysis, lexical analysis, so how your compiler understands the input program. And he'll also talk a bit more about the runtime organization of a program. So in particular, how the stack, the heap, how records and object-oriented programming and so on are implemented. Course materials are available through the materials website, through Panopto, of course. I also very strongly recommend the textbook, and I'll come to that shortly today. The course web pages for my half of the course are here, and we will endeavour to support you in continuing discussion of topics in the course, questions and so on, through Piazza. So this course is about a particular kind of program, a very special kind of program in my opinion. It's about language processors, it's about compilers, it's about programs that process programs. So programs are written in some programming language, and so the heart of the compilation problem is to understand programs and the language in which they're written. Compilers also write programs in some other language. They have a source language in which the input arrives and a target language in which code is going to be generated. Usually we think of that as being a lower level language, perhaps even assembly code or machine code. And compilers, fundamentally what they do is they translate code written in one language into programs written in another language, hopefully in some sense equivalent programs. The meaning is preserved, but perhaps mapped from the higher level representation, the higher level language, to the lower level language. And so a compiler is a tool that enables you to program at a higher level by mapping higher level programming language concepts to low level implementation. And consequently, understanding compilers is a pretty essential part of understanding the kind of technology stack involved in how programs actually get executed, and consequently your training as a software engineer. So compilers in abstract terms take source code as input and produce output in some target program language. So a concrete example might be a compiler that takes as input a program in Haskell or C++ or Java or something, and as output it might generate x86 assembly code or ARM assembly code, or there are even compilers that generate high-level code as output. And it's very common, for example, to take a high-level language and compile it to C. But you might even try and compile a high-level language to another high-level language. So, for example, people have looked at compiling C to JavaScript, for example. Another key function of a compiler, of course, is to support programmers by telling them about their programs. So the compiler is going to analyze your program in order to generate good code. And as it analyzes, it might discover things that aren't right. And so a key part of building good compilers is that they produce helpful error and warning messages when something doesn't make sense in the input code. So compilers translate from one language into another. They output a low-level program which behaves as specified by the input higher-level program. And more abstractly, they mediate between the higher-level human concepts that we want to be talking about when we write our programs and the word-by-word, bit-by-bit, instruction-by-instruction data manipulation that the machine actually does. So what does a compiler actually look like inside? Well, there are things we can obviously infer. There's input in some language. There's an analysis phase of the compiler that constructs some kind of internal representation of the source program's structure. And we'll talk a little bit about what those representations might be. A common one is a tree, often called the abstract syntax tree, the AST, the abstract syntax tree. Actually, also, we will talk later in the course about other representations, like control flow graphs. So the compiler consists of a half that analyzes the input, and then the other half synthesizes the output. So having constructed this representation, the second half of the compiler uses that and walks that internal representation to construct the output code, to generate the output code. So in a little bit more detail, here's another way of drawing that picture. So as I said, there are two halves. There's an analysis half and a synthesis half. And in the middle is our representation of everything that we learned in the analysis half that we're going to use for program synthesis. So there's abstract syntax tree describing how control structures are nested one inside the other, for example. And there's a symbol table which tells the compiler is where the compiler records everything that it has learned about the names that you defined in your program. So the variables, the functions, the methods, the classes, the objects, and so on. So the analysis half of the compiler begins with lexical analysis, where you find the elementary lexical classes. Is this an identifier? Is it a keyword? Is this punctuation symbol meaningful in your programming language? Syntax analysis is where we unpick the nesting structure of the program. So obviously we know that loops can appear inside loops. If-then-else statements can appear in a nested form. We could have loops inside if-then-else's inside loops inside if-then-else's. We can have nested structure, and that leads to the abstract syntax tree that I told you about. And so the job here is to discover that tree structure. Semantic analysis is a general term for how we keep track of what the program really means, and consequently, for example, does the program have a type error? Or if we use an operator like plus on two variables, a plus b, is that supposed to be an integer addition, a floating point addition, or a string concatenation, or what? And for that, you need to know what the types of the objects are, and that's what semantic analysis is for. So all of that leads to a point where we have a symbol table describing all the names, all the types, and so on, and we have the abstract syntax. And then we can walk that abstract syntax tree, consult the symbol table, and generate code. And in simple non-optimizing compilers, the kinds of compilers that we'll see at the beginning of this course, this is actually pretty much a direct pathway. We walk the tree, we generate the target code. More sophisticated compilers build some kind of intermediate representation here, perhaps a control flow graph, as I mentioned to you earlier, in order to do optimizations. And the optimizations that we're going to look at, well, the main optimization we're going to get to later in this course is loop invariant code motion. Loop invariant code motion is the idea that we're going to identify expressions inside a loop that don't actually have to be executed, evaluated every time we iterate that loop. Instead, we can evaluate that expression just once and reuse that value inside the loop. So loop invariant expressions, our job is to find them and lift them out of the loops in order to make your programs go faster. And we're going to get to that later in the course as a kind of illustration of the kinds of optimizations that a compiler might do. There are, in fact, many more optimizations compilers do. And so having constructed intermediate code from the abstract syntax tree, we might apply various optimizations, and then eventually we'll generate code, for example, assembly code, perhaps in assembly language, or even directly into machine code. In this course, we're actually going to concentrate on compilers that take as input some high-level imperative language, like C or Java or something like that, and as output, generating assembly code, so human-readable code that you need to run your assembler on. So people often think of that compiler structure as a sequence of things the compiler has to do, phases of a compiler. So we have lexical analysis, where we convert the string of characters in the source code into a string of symbols. I'll show you what I mean by that in a moment. And then we construct the abstract syntax tree. I'll show you an example in a moment. And we do semantic analysis. We might just do type checking, for example. And as we go along, we construct and maintain a symbol table representing everything that we know about the variables and names and classes and so on. So I call these phases because you could think of doing all of this and then all of this and then all of this in a sequence of separate sweeps over the entire input program. More normally, they're interleaved in some more complicated way, but they're conceptually separate phases, and in particular they operate on conceptually different representations of the program. So let's get concrete about that. Let's try it with a little example program. So in this file test.c, I have a little C program, the smallest imaginable C program, I think. We declare two global variables, and then in this function we add 123 to b to produce a new value for a. So you could type this in, cut and paste it from my lecture slides, and run your favorite compiler on it. For example, the GNU C compiler. If you give it the -S flag, then what it does is, instead of generating executable binary code, it actually generates human-readable assembler code. And so here is the test.s file that you get if you run that command. Incidentally, the -O flag here tells the compiler to do some simple optimization. And I'll show you the effect of that in a few moments. But what it does for us here is it simplifies the output code slightly. So what happens? The declarations here turn into assembly code to reserve 4 bytes for each of these two variables, because they're integers, they're 4-byte integers. And this block of 4 bytes is labeled A, so the address at which the assembler chooses to place those 4 bytes is called A, and here's B. Then here is the label for the entry point for the test for the assembly code version of the C function that we had over here. What does it do? Well, it pushes the base pointer onto the stack. It pushes the old base pointer onto the stack, and then it updates the base pointer with the current value of the stack pointer And then over here at the end, it undoes that. It pops the base pointer that it saved. What it's doing here is it's constructing a new stack frame for this function. It turns out in this really simple program that we don't really need the stack frame. But when you don't add any further optimization flags or anything, you get a stack frame constructed for every function anyway. This also helps the debugger as well. So the main body of the function is in here. What does it do? It moves B into this register, adds 123 to it, and then moves the register to variable A. It does exactly what the C program says. So your job as a compiler writer is to build a compiler that can convert that to that. And you will, through this course and through the WAC exercise, the compiler lab exercise, absolutely learn how to do that. In fact, you'll learn how to compile much more complicated programs than this one. So how does a compiler actually do this? Well, the first step, as I mentioned to you before, is lexical analysis. So lexical analysis is where we take the input sequence of characters, int, space a, semicolon, new line, int, where we take that sequence of characters and we turn it into a sequence of tokens. Tokens are things of relevance to the programming language as a list, as a sequence. So they're unstructured, but we know what they are. So we've identified that int is a keyword in C, and so we have an integer token type here. An identifier is anything that's any string of characters that could be a name that's not a keyword. And so A is identified during lexical analysis as a new name that the programmer is using. So when the lexical analyzer encounters this name, it allocates a space for it it allocates an entry for it in the symbol table, in the compiler's symbol table. So this is where the compiler will keep track of whether it's what type this variable has, for example. Next, we have a semicolon. So the lexical analyzer tells us that it's found a semicolon, and another instance of the integer of the int keyword, and so on. Here is main. So main is another identifier. Again, the lexical analyzer only knows that it's a new name that has occurred, a new identifier that has occurred in the input. So it allocates the entry for it, but we won't discover what kind of thing it is until later when we do syntax analysis. Okay, so that's lexical analysis. Now let's look at syntax analysis. So syntax analysis is often also called parsing. They really mean the same thing. Is about a definition of a programming language that looks like this. And I imagine you might have seen something that looks a bit like this before. This is often called Backus-Naur form. It's a notation for grammatical rules. It actually builds upon a thing called context-free grammars, which goes back quite a lot earlier than its use in computing, actually. It was used for describing natural languages like English or Russian. But anyway, so Backus-Naur form, the key idea here is that what this rule says is that anywhere where you can have a stat, a statement in your programming language, anywhere you can have a stat, you could have one of the different kinds of statements in your programming language, right? So it says that anywhere you can have a stat, you can have either a print statement or a while statement, a while loop actually, or, and this one here is an assignment expression, right? So expression here is another of these things. These things are called non-terminals. These are the things that are being defined by rules like this one. And there are going to be more rules like this one for expression, for example. So a statement could be a print statement, and this would be whatever sequence of lexical tokens makes up a valid expression in your language. It could be a while statement, in which case there's a condition here represented by some other sequence of lexical tokens that forms an expression. And then there's a loop body, right? And the loop body is another statement. So these things are recursive, they're often recursive, and that's how we get a tree structure or a nesting structure in our program. Okay, so the function of syntax analysis is to basically use this backwards to extract the grammatical structure from the input program, to work out how the BNF rules must have been applied to give you the input you've actually got. And if the compiler can't do that, it's because there's a syntax error in your program. So the job of the syntax analyzer is to check that the input is syntactically correct, but also to construct this tree representation that we need, the abstract syntax tree. So let's look at that in concrete terms. Here are the input characters for a fragment of a C program. Here are the lexical tokens. So you can think of this as a list, like a Haskell list of the sequence of lexical tokens here. Identifier, equal sign, identifier plus, constant number, right? And then syntax analysis understands this as, by decoding it using the BNF, to extract the tree structure, the nesting structure. It discovers that this thing is a assignment statement with a left-hand side here, which is an identifier, and the right-hand side, which is this expression. So for more complicated examples, we get bigger and more complicated trees like this. And we're going to implement this tree in the obvious way as a tree of linked objects in your programming language, in your compiler implementation language. And your job as a compiler writer, as a compiler architect, is to design the abstract syntax tree data structure to be easy to build during parsing, during syntax analysis, and easy to use. What are we going to use it for? We're going to use it to generate code. So you want to try this. You can, as I mentioned to you before, make a C file, compile it with your favorite compiler, like the GCC compiler with the -S flag. And I recommend adding the optimization flag. And you can look at the output. You can even add additional compiler flags like this one, emit frame pointer, which simplifies the output a bit because it gets rid of those EBP operations. You can try it on Windows, but actually, easier than all of that is to use this fantastic website called the Compiler Explorer. This is quite helpful if you ever get stuck trying to figure out what your program is doing and what the compiler has actually implemented given the code that you wrote. But for many purposes, it's actually easier to look at this website, the Compiler Explorer. So here it is, here's the URL. What it does, you type in your code here, your C program, on the left, and then you select which compiler you want to use. So I've told it that the input language is C++, that the compiler I want to use is the Clang compiler version 11. I've not given it any compiler options yet, but we will in a moment. And here, it automatically and instantaneously gives you the assembly code corresponding to that input. So have a look at this and see if you can understand what the compiler has done. To help you, the output is color-coded to correspond to the input. So the green and grey parts here are what happens at the beginning and end of a function. What you can see is that they're setting up the frame pointer. RBP is a pointer to the current activation record on the stack, the frame. And so the first thing that the compiler does is it stores the caller's frame pointer, then it sets up the frame pointer for this function using the current value of the stack pointer. And then at the end of the function, it restores the caller's version of the frame pointer. Then we can look at the body. What does it do? It loads data from location B into EAX, into a register. It adds 123 to that value, and then it stores that value to variable A. That's exactly what you had expected, right? Let's look at a slightly more complicated example. This loop is kind of similar, but it works on a whole array of elements of A and a whole array of elements of B, and it adds 123 to each one. And again, the color coding helps. So here's the frame pointer set up and restore again. Then this yellow part refers to the loop infrastructure. So this part is initializing the loop control variable I, and this part is checking whether I has exceeded the loop bound yet, and this part increments it and jumps back. So where is I stored? It's stored in the activation record, in the frame, in the current stack frame. So the RBP value is the frame pointer. RBP minus 4 is where I is going to be stored in memory on the stack. And we start by initializing that to 0. Then we compare that to 2024 and exit if the condition if the exit condition is satisfied. Otherwise, we fall straight through into the loop body. We use RBP, we load the I value into RAX and then use it as the address for this load instruction, multiplying it by 4 because there are 4 bytes per int, and adding it to the base address for the array B. We do the add, then we store the value back in the same way. Then we increment the loop control variable and go around again. Okay, this is the code that you get if you run the compiler without giving it any optimization flags. So this is equivalent to an optimization level of 0, minus O0. And what the compiler is doing here is exactly what your compiler could do, right? I will show you, I will teach you, we will teach you how to build a compiler that generates code that looks a lot like this. What's nice about this is there's a direct correspondence between the assembly code and the source code. This is called syntax-directed translation. The syntactical structure of the source code is evident in the structure of the generated assembly code. The other nice thing is that at any point in this program, you could stop, perhaps in a debugger, and you could print the current value of I, because you know where it is. It's in the stack frame. If you increase the optimization level, excuse me, here are some comments to explain what I've just told you, but I have just told you them. If you increase the optimization level to minus 0.1, you get much simpler code, but it's done something a little bit subtle. Variable I is basically stored in register RAX, but actually it's initialized to minus 4096, and it's incremented by 4 each time. So it's incremented by 4 each time because actually it's going to be used in the address calculation. It's going to be added to the base address of A. And so we're going to bump that by 4 bytes into each iteration. And it's initialized to minus 496 so that there's no need for a compare instruction here, because this jump instruction here checks whether the result of the add was equal to 0. And if it wasn't, we go around the loop again. Okay, that's minus 0.1. What happens if you increase the optimization level further? Well, in that case, things can start getting complicated. Let's see if we can unpick what's going on here. And maybe we should step back and you could look at this, right? You could stop the video at this point and see if you can understand the code that's been generated. There are some things I should tell you. This code is using vector registers. It's using these XMM registers that store 4 values at a time. So XMM is being initialized. There's a helpful comment generated in the assembly code by the compiler to tell you what's going on here. It says that XMM0 is being initialized to the constant 123, 123, 123, and in fact that constant is defined up here. So this is a register containing 4 copies of 123. You can think of the register as consisting of 4 lanes, one each beside the other. And the subsequent instructions compute on a block of 4 adjacent values from the array A, from the array B. So this load instruction here initializes XMM0. This load instruction here loads a block of 4 values from this address, which is the start address for array B. This add instruction it's a packed add. So what it does is it adds corresponding elements from XMM1, from memory, to corresponding elements of this XMM000 register to the 123, right? So the 0th element of this vector is going to be added to this value, the first, the second, the third, and so on, in a pointwise way. So that produces a value for XMM1. XMM1 is stored over here, right? So this is the store instruction that stores that value back to memory. So the really strange thing is that where do these other instructions come from? Well, so we can look at what happens to XMM1 here, and it's loaded, incremented, and then stored here. In fact, XMM1 is reused in this code here. It's loaded, incremented, and stored back here. What we're seeing here is that there are actually 4 copies of the loop body here. Each of them vector-wide, but there are 4 copies of that code, and the instructions are interleaved by the compiler. So the compiler has unrolled this loop 4 times and scheduled the instruction, presumably using some model of which instructions, of the processor's pipeline, of how the processor hardware is implemented. So when we get to the end here, we increment the loop counter by a big number. We increment it by, well, it's 4 bytes per int, this we knew. There are 4 ints for each XMM register, right? And then we're unrolling the loop 4 times. So we get 4 times 4 times 4, which gives us 64. So that's the code generated by the Clang compiler version 11 with -02. This is the same input running with a different compiler, with the Intel compiler, commercial closed source compiler from Intel. And they have this fantastically named compiler flag -fast, which basically means use all the compiler flags to generate the fastest possible code, specialized to run on the particular hardware that this compiler is running on. And as a consequence, it's chosen to use not XMM registers, but YMM registers. YMM registers are like the XMM registers, except instead of being 4 wide, they're 8 wide. So the code kind of works the same way. We initialize YMM0 with this value, which comes from here, which is 8 copies of hex 7b, which is 123. Forgive me, they spilled off the end, but trust me, there are 8 of them. And then this add instruction accesses its data direct from memory using rex times 4 plus b. So rex is the loop counter again. And what happens to YMM1? It gets stored back in this instruction. There are actually, there's an the code is also unrolled, but this time only by a factor of 2. And the compiler has scheduled the 2 iterations to separate them. So there's an add and then a store, an add, then a store. Okay, so that's the Intel compiler's version of this. Different compilers do different optimizations. They make different instruction selection decisions, and they may choose to eliminate or transform the loop control variables, for example, in different ways. So I've shown you a little bit of compilers at work, and what I've shown you is the classic compiling a language like C to a machine code like x86. There are lots of other things that you could do with a compiler. In fact, one of my favorite things to do with the compiler, in fact, one of the things that I do a lot of in my research group, is domain-specific optimizations. And in order to deliver domain-specific optimizations, you very often need a domain-specific language of some kind to capture the structure of a particular application domain, a family of problem instances, hopefully at a higher level, and certainly in a way that enables us to do optimizations that would have been hard to do in a conventional programming language. So a classic example of that would be something like TensorFlow. You might tell me, TensorFlow, hey, TensorFlow is just a Java library, just a Python library, but you can think of TensorFlow as an embedded domain-specific language. As a programmer, what you do in TensorFlow is you construct a data structure representing the deep neural network that you're trying to train, for example. And that runtime data structure is essentially forms a language, an embedded domain-specific language. There are lots and lots of examples of this, and the list can go on and on and on. Because actually this is a really powerful software engineering technique to recognize a family of problems. And instead of building a parameterized software solution, you build a programmable software solution. Give you an example, network routers these days are commonly, often, at least from in the advanced kind, programmable, and P4 is a domain-specific language, especially for network packet forwarding policy programming. Solidity, a language for blockchain contracts, and of course you can execute Solidity contracts, but you might also ask other questions about them, like is it safe? Does it have a race condition in it? Given some expectations about future market conditions, can you evaluate the current estimated value or distribution of values or probability of an option being underwater or something like this? GLSL you may have come across for coding shaders. SQL I know you know about. Verilog, a domain-specific language. Well, it's a general purpose programming language, but it's specifically designed for, for describing digital circuits. And there are many, many, many more. This one is a little bit more obscure. It's one of my research projects. It's a domain-specific language where we invite applied mathematicians in computational science who are doing things like simulating the way glaciers flow, for example. They type in their partial differential equation, and we generate the highest possible performance code from their equations. Finally, there are domain-specific languages actually for compiler construction. One family of such things that you'll learn about is parser generators. So Yak is the famous one, yet another compiler. Antler is a Java parser generation tool. There are many more. These are tools to help you building the front end of a compiler, the analysis side of a compiler. TableGen is a domain-specific language that forms part of the LLVM compiler suite, and this is part of the compiler's backend. What it does is instruction selection. You specify the instruction set for your target processor, and TableGen automatically generates an instruction selection implementation that tries to find the most appropriate instruction to use at each point based upon what the programmer actually wrote and how it's represented in your compiler's intermediate representation. So these are all compiler projects in a way. There are things you might do that look like compilers but aren't actually compiler projects. A classic one is something like find bugs, which is a tool that analyzes Java class files looking for either signs of actual bugs or at least signs of suspicious program behavior that the programmer should be aware of because they're associated with bugs. And there are several such things. Coverity and Code Sonar are commercial products being used to some extent to find bugs in a similar way, but also actually for security vulnerability analysis. And there are lots more. CLE is a project actually led by a colleague of ours at Imperial College, Christian Kadar. And this is a symbolic execution engine. So it's kind of like an interpreter for, well, actually it's an interpreter for the LLVM intermediate representation. So it forms part of the LLVM compiler, but it enables you to execute a program without knowing what the input values are. You treat the input values as symbolic, and it computes the symbolic expressions that your program would execute on. And there are many, many more. So, moving on, let's talk a little bit about how the course is structured and consequently what you might hope to actually gain from it. So, as I mentioned, the course is taught jointly by me and Naranker Dulay. And the course will be interleaved with contributions, lectures from him and from me. I will begin with an introduction to the overall structure of compiler. I'll show you a complete compiler from beginning to end, entirely all the code in PowerPoint slides. And along the way, I'll introduce syntax analysis, and we'll look at how to build a parser, a syntax analyzer, a lexical analyzer, and so on in the simplest possible way. Naranker will pick that up and dive into the theory for the automated tools that support you in building lexical analyzers and parsers, parser generators, things like Antler that I mentioned to you a moment ago. And from that, he'll show how to use tools like Antler to build the abstract syntax tree. And from there, he'll talk about how to walk that tree and not only generate code, but also check that the program is constructed correctly, that it doesn't have type errors, for example. A key thing that he will also show you is how to manage the symbol table. So when I introduced the basic structure of a compiler, I suggested the symbol table was a flat data structure that just records the names in your program. But it's clear that that's not enough for interesting programming languages with concepts like scope. He will then finish with looking at the runtime organization, how objects are allocated in object-oriented programming languages, how methods are invoked on with inheritance, for example. And he'll finish with a little bit on garbage collection, a fundamental thing that I think every software engineer should know something about. My side of the course begins with code generation. So I'll show you how to build a simple code generator that walks the abstract syntax tree and generates code. This is what I referred to a moment ago as syntax-directed translation. We'll then look at how to generate better code. And we'll begin with looking at register allocation. We'll look at a really simple technique for quick and dirty, but very effective register allocation. And then I'll show you the classic graph coloring register allocator. And one of the reasons to show that is because it introduces the problem of finding which variables are live at each particular point in the program. And that's a data flow analysis. We'll see more of data flow analysis when we look at optimizations, and we'll build up through reaching definitions and live variable analysis to loop optimizations, in particular lifting redundantly executed expressions out of loops. a fundamental code motion optimization, and an introduction to the larger world of more sophisticated program optimizations. So putting all this together, it should give you not only a map of the compiler topic and a much clearer idea of what compilers do, how they work, and what the theory they build on, but also give you a sound foundation on which to build your own compiler in the WAC lab exercise. That brings us to wrap up with the topic of how to succeed as a student in this course. I hope I've given you some of the reasons why you should want to succeed in learning more about compilers. Here's where I'm going to try and tell you how to be a successful student. And the first thing I want to talk to you about is textbooks. So my objective in inviting you to refer to a textbook is for you to become an expert through this course in the broader topic of compilers. And when I say expert, I don't mean that you need to know everything that's in the book. What I mean is that I hope that by the end of this course, you will know enough about the topic to have a map of it in your mind. And a map of the textbook is a pretty good notion of a map of the topic. So this course is not closely based on any particular book, and there are a couple of good candidates. Here are a couple of good candidates I'm going to mention. Over the next slide, I'm going to tell you which is our actually recommended book. But let me just tell you about these for a moment. So this one, it's called The Dragon Book. If you look carefully, you'll see there's a picture of a dragon on the front. And if you look really carefully, you see that it's a knight in shining armor fighting the dragon of complexity of compiler design. So when you come to build a compiler of your own, you'll discover that compilers can get quite complex. And the objective of this book was to help you control and manage that complexity. This book is called The Dragon Book, and it is the classic textbook on compilers. It's quite thick. It's thicker than we really need for this course. And it covers all of the topics that we're going to cover and many, many more. Compiler engineers, professional compiler engineers, think of this as almost a religious text. It's the Dragon Book material is stuff that any compiler engineer should know about. In contrast, I found this book very helpful, particularly in preparing some of the lectures for the course, actually. Andrew Appel's Modern Compiler Implementation in Java, because it takes a completely different philosophy. Rather than giving you an encyclopedia of all the different things you could do, all the different compiler engineering techniques that you might wish to know about, what he does is he tackles a specific project, a class project he's developed as a lecturer, as a professor at the University at Princeton. And he tells you what choices he made and what choices he recommends. He doesn't tell you very much about the alternatives, but he does tell you why he chose what he chose. So those are the books that are pretty good books, and you could do well by working with one of those books. The book we actually recommend is this one, Engineering a Compiler by Cooper and Torzon. Some reviews, well, the usual stuff, I suppose. My favorite one is this one. If you're a beginner, do not buy this book. I include this one, not because I think it is a reason why you shouldn't buy the book, but instead to recognize that by the time you've finished this course and built a compiler of your own with the WAC exercise, you actually will be beyond a beginner status as a compiler engineer. You will actually have hands-on experience of building a compiler yourself, and consequently, I think this might be the book for you. So to wrap up, let's just talk about what I think will help you succeed as a student. And you shouldn't take my word for it. You are all seasoned and expert students, right? You're good at this. You're good at studying, you're good at passing exams and so on. Use the textbook and don't save it for the end. Use the textbook to get a head start. All of the textbooks begin the same way as our course will begin, which is through a walkthrough of the simplest possible compiler from beginning to end. I do that in the next lecture, and they do it in the first chapter or two in each of those books that I've mentioned to you, actually. And next thing is to do with being an active learner. So make notes as you listen to pre-recorded lectures like this one. Make notes about questions, about things to look up, things to follow up, things that you found confusing, or even perhaps things that you found interesting. We also will be providing tutorial exercises, and I strongly encourage you to do them. The exams are set on the assumption that you will have done the tutorial exercises. The exams are also set on the assumption that you've done the past papers. So you are assumed to have studied the past papers. Make sure that you do. In fact, I would strongly recommend that you go look at them now. I'd recommend you do that for all of the courses that you're taking, just to get an idea of where we're going, what the future will hold, what it takes to pass and do well in the exam for this course. Make use of the opportunities for interaction and feedback. We will be running live Q&A classes, and through that you should be able to get some feedback on your solutions. Piazza is the other key vehicle for what we're doing here, and I strongly encourage you to take advantage of that. We will try to be responsive. I hope that students will also answer and comment on other students' solutions, and that should lead to an actually more interesting and engaging experience for everybody. Finally, there are many courses like this around the world, and their course materials are very often on the web. So if you find something confusing or difficult in one of our lectures, you can go look at the textbook. You can also go and see the lecture slides for other lecturers, other professors around the world who have taught similar courses, and see if their explanation makes more sense, or indeed whether they tell the story in a different, more helpful way. If they tell something that's factually different, let us know. But use the resources available to you and be an active learner. Okay, thank you very much indeed. That brings us to the end of today's introduction to the course, and I look forward very much to seeing you in January in our live classes. Till then.